Compare a rigid, perfectly transparent beverage bottle with a spool of opaque, highly flexible textile yarn. These two materials dominate their respective global markets. The clear plastic accounts for about 30% of the world's packaging demand, while the flexible yarn makes up over 60% of the entire synthetic fiber market. They look different, they feel different, and they behave under stress in entirely contradictory ways. Yet they are chemically identical, both made from the exact same repeating macromolecule. That molecule is polyethylene terephthalate. It consists of repeating units of 10 carbon, 8 hydrogen, and 4 oxygen atoms. The utility of this material is not determined by its chemical composition alone. To achieve those extreme physical differences, engineers rely on the material's thermal history. In polymer science, the processing defines the property. Industry recognized the strength of this polymer early on. Its first major commercial success was in textiles, where it was spun into opaque, high-strength fibers. Marketed under names like terephthalate and dacron, this specific form became universally known as polyester, used to create durable and wrinkle-resistant apparel. Beyond apparel, engineers developed methods to use PET as advanced film bases, electrical insulation, and high-pressure barriers. Moving from simple textile weaves to advanced barrier-grade films required an exact understanding of the polymer's internal morphology. Producing this material at scale generally follows one of two industrial pathways: the dimethyl terephthalate, or DMT, transesterification process, and the purified terephthalic acid direct esterification process. In both cases, the primary chemical is reacted with ethylene glycol under extreme heat and vacuum conditions. During this polycondensation phase, removing the resulting water or methanol byproducts is mandatory. Extracting these byproducts drives the reaction forward, enabling the creation of a high molecular weight polymer. The defining mechanical feature of the resulting polymer backbone is the aromatic ring located directly within the terephthalate unit. This hexagonal structure is bulky. Its size and placement severely restrict rotational movement within the polymer chain. Because the chains cannot easily twist or fold, the polymer maintains a high baseline tensile strength and dimensional stability. While the chemical backbone provides raw potential strength, the material's physical characteristics are only finalized during the next stage of thermomanipulation. To decode exactly how a polymer behaves under heat, engineers use differential scanning calorimetry, or DSC. This is a typical DSC thermogram for PET. The first critical thermal landmark occurs between 67 and 81 degrees Celsius. This is the glass transition temperature, where the rigid material first becomes pliable. As heating continues, we hit a sharp exothermic peak at roughly 148 degrees Celsius. This is the point of cold crystallization, where the polymer chains begin to organize themselves. Finally, at the extreme high end, between 250 and 260 degrees Celsius, we reach the melting peak. Here, the crystalline structures completely break down into a viscous liquid. The temperature gap between the initial glass transition and the final melting point is the manipulation zone for industrial processing. Precisely timing the cooling process within these specific thermal boundaries dictates exactly how the polymer chains organize physically. To produce transparent containers, the viscous molten PET is cooled at an extremely rapid rate straight from the melt. This is a process called quenching. Because the temperature drops so quickly, the polymer chains are frozen in place before they have the thermodynamic energy required to organize into structured patterns. This chaotic, unaligned molecular structure is known as the amorphous state. In this state, the crystalline particle size is near zero. Since this is well below the wavelength of visible light, light passes straight through the material without scattering. This combination of optical clarity and structural flexibility is utilized for optical films, blister packaging, and shatterproof beverage bottles. In the amorphous state, thermal speed suppresses crystallization, trading structural rigidity for absolute optical clarity. To create high-strength fibers, manufacturers use slow cooling combined with mechanical drawing, such as extruding the melt through the tiny holes of a spinneret. Sustained heat alongside mechanical stretching forces the polymer chains to untangle. They align into highly ordered parallel structures. This highly organized structural state is called semicrystalline. Through precise extrusion, industrial processes can push the material up to 60% crystallinity. There is an optical trade-off. This dense, ordered alignment scatters incoming visible light, rendering the crystalline material completely opaque and white. However, the parallel alignment causes an exponential increase in tenacity and modulus, generating the material's characteristic high tensile strength. By altering the cooling speed and applying mechanical stress, industry engineers an entirely distinct, ultra-strong material from the exact same molecule. The same molecular packing that provides PET with its strength also produces exceptional barrier properties. This density grants the plastic high dielectric strength and critically low gas permeability, effectively blocking the passage of oxygen and carbon dioxide. These specific barrier properties are why PET is the standard for packaging pressurized carbonated beverages. The stable ester bonds that protect food from weak acids and oils also make the plastic highly resistant to biological degradation. Managing this stability requires chemical recycling methods like glycolysis and hydrolysis. These processes apply targeted heat and chemicals to depolymerize the chains back into their raw monomers. The chemical resilience that makes PET an unparalleled packaging material is the exact same trait that makes its end-of-life management a severe engineering challenge. The global prevalence of PET stems from precise thermomechanical control over the specific chemical backbone. It demonstrates the leap from merely creating chemical bonds to actively engineering purpose-built morphological states. Ultimately, in the realm of advanced polymer science, the thermomechanical processing of a material defines its final physical properties.